Hello everyone, this is Tianwei. I'm presenting our recent work, end-to-end sequential sampling and reconstruction for MR imaging. This is a joint work with my co-first authors Zihui Wu, He Sun, Adrian Dalca, Yisong Yue, and Katie Bouman. Magnetic resonance imaging, or MRI, is a common medical imaging technique. It generates images by taking measurements in the Fourier K-space. K-space is an array of numbers representing the spatial frequency information of an object. The central challenge in MRI is its slow acquisition process, which leads to high cost, patient discomfort, and reconstruction artifacts when the patient moves. Accelerated MRI mitigates this challenge by only measuring part of the K-space to reduce acquisition time. We aim to recover a good reconstruction from these partial measurements. Two challenges arise in this subsampling scenario. One is around the sampler. Which parts of the K-space do we want to measure? Since different structures in the image show up in different frequencies, the sampler needs to sample one set of measurements over the other to accurately reconstruct different types of images. The other challenge is around the reconstructor. How to reconstruct a high-fidelity image from partial measurements. These two challenges are intercorrelated, and a good reconstruction stems from the cooperation of a sampler and a reconstructor. Recently, deep learning methods have gained increasing popularity and shown state-of-the-art performance on mitigating both challenges. Previous deep learning methods can be organized as two general approaches. The first line of research takes advantage of the differentiable nature of neural networks. Instead of only training the sampler with a fixed reconstructor, this approach performs end-to-end training on both the sampler and the reconstructor. We call this the co-design approach. The second group of methods consider the sequential nature of MRI sampling. Since in actual MRI scans, measurement cannot be taken all at once, we should be able to leverage intermediate information to guide later sampling. This approach takes advantage of sequential decision-making over predetermining all measurements in advance. Methods in this approach models the MRI sampling problem as a partially observable macro decision process and applied reinforcement learning method to solve it. We call this active sequential approach. In our work, we propose a framework that integrates these two approaches to designing a deep sampler. Instead of predetermining a sampling pattern, our method provides adaptive sampling for individual patients. How is this done? We first sample a few measurements to get a rough reconstruction. Then, our learned sampler will sequentially estimate the next best measurement to take based on the previous steps. Sequential sampling allows our models to leverage intermediate information for later sampling. We also take the co-design approach to jointly optimize the deep sampler and the deep reconstructor through end-to-end training. In the following, we'll denote the number of sequential sampling steps as T, so that one-step method means that there is only one adaptive sampling step where we take all measurements, while four-step model performs adaptive sampling 4 times and we take a quarter of the measurements each time. In experiments, we investigated the 1D line and 2D point sampling scenarios using the FastMRI single-coil knee dataset. We compare with baselines under the same acceleration factors. Acceleration factor represents the ratio of measurements to take in comparison with the total number of measurements. An acceleration factor of 4 means that we take a quarter of the total K-space samples to reconstruct the image. Now, I will show you some of our experimental results. Firstly, here are some quantitative comparisons of our models versus the state-of-the-art learned K-space sampling baseline LOUPE. LOUPE also co-designed the sampler and reconstructor, but it is not adaptive and performs sampling in one shot. For both 1D, 2D sampling scenarios and various acceleration factors, our sequential model that performs sampling in 4 steps significantly outperforms non-sequential LOUPE. The average reconstruction SSIM on the test set steadily improves as the number of steps increases, which further shows the advantage of sequential sampling. Second, the improvements are consistent across the whole dataset. In this plot, the x-axis is the amount of improvement in SSIM our model have over the loop baseline, and the y-axis is the number of samples corresponding to different improvements. Our one-step model already outperformed LOUPE on more than 75% of test samples in both 1D and 2D settings. The percentage of improved samples steadily increases as the model takes more sequential steps to perform sampling, reaching around 97% with 4 sequential steps. These results show the significant and consistent benefit of sequential sampling. Third, we compared our method and 2 sequential but not co-designed baselines. We show the sample-wise improvements of these 3 methods over LOUPE. We see that these 2 sequential baselines that don't co-design with the reconstructor in an end-to-end framework only outperforms LOUPE for 1.6% and 5.6% of the samples. In contrast, our method significantly outperforms LOUPE for 97% of the samples. So Sampler-reconstructor co-design in an end-to-end differentiable framework is crucial for good performance. To understand the improvements better, we visualize our trained model's behavior with different inputs. Here, we show the full acquisition process and final reconstruction of our 4-step sequential model with left and right rotating knee images as inputs. The pink areas are the selected measurements. We can see from the 4th column from the left that our model is aware of the input rotation and can sample measurements accordingly. Note that our model is not trained with any rotating images, but still learns to adapt to rotations. Here are some visual examples of our method and other baselines in the 1D setting with 4x acceleration factor. In this setting, we sample a quarter of the case-based data to perform reconstruction. Our reconstructions are often more accurate with more detailed local structures. For example, the white areas pointed by these arrows are wiped out by other methods but accurately reconstructed by our method. This visual example compares our method and other baselines in the 2D setting with 8x acceleration factor. The lines pointed by these arrows are disconnected in other methods but accurately reconstructed by our method. One ongoing work we are exploring is to optimize our method to produce reconstructions that best preserve details near pathology region. We believe that our sequential method will be especially valuable in this setting through a classify and sample framework. We want to build a sequential sampling pipeline that identifies the specific pathology in early steps and adapts the sampling pattern to this specific pathology. We performed some early analysis to verify the importance of adaptive sampling in this setting. We use a recent FastMRI Plus dataset, which adds pathology box annotation to the original FastMRI dataset. And we want to optimize the image structures in the pathology region instead of the whole image. Under this setting, we find that optimal sampling masks for different pathology tend to be drastically different. Here we show the non-probability mask for a few common knee diseases. Larger value indicates a higher likelihood to select this specific case-based region. The best undersampling mask for samples with knee cartilage defect tends to have explicit vertical structure, while the sampling mask for ligament sprain tends to be mostly horizontal. Other pathologies like bone fracture and meniscus tear has shapes that lies in between the purely vertical or horizontal structures. We believe this highlights the importance of adaptive case-based sampling for accurately reconstructing pathology regions. In summary, we have presented a new framework for accelerated MRI sampling. We believe that future accelerated MRI image methods need to be adapted and co-designed with the reconstruction model. This will enable the model to get the most out of limited measurements due to scanning time and cost constraints, Please check out our website for more details.